Good evening, class. You are welcome to today's lecture. We are continuing with our course on artificial intelligence. My name is Linda Moakon, and we are starting with the first part on searching strategies. We are going to have the following learning objectives for this particular course. One, we will try to understand the essence of search, why we need to do search in the first place. Then we will look at some examples of search and what they entail. We will know how to formulate search problems, and then we'll see different types of search problems that we can have. Right, what is search? When you are searching for something, it takes you effort to look for something desirable that you are looking for. It entails exploring all possible solutions before you take an action that is intended to solve a problem. When we are carrying out a search, we need to be able to tell that the decision we have arrived at is the best decision we could take. And we can't do that unless we have evaluated all possibilities and seen what they also entail before we can convince ourselves that what we have chosen is the best that we could choose. Now, search is important for tackling problems for which a direct method is not known. And by direct method, I mean that you can't easily tell whether you move from A to B is a solution, moving from C to D is a solution. If you have to explore a number of opportunities or possibilities before you decide, that is when you need to undertake a search. Now, we need search because we need to also tackle problems intelligently. What that means is we don't want to run around like a headless chicken not knowing what we are doing. We need to be able to convince ourselves that we have brought on board our experience, our foreknowledge, and everything else. We've been able to consider everything else before we have concluded on the solution for a search problem. Examples of search. When you are playing chess, chess is a board made up of white and black squares. You need to think 2 or 3 steps ahead of a move before you make the move. And in so doing, you need to evaluate the desirability or the utility function of every move that you intend to make. So if before you move from square 1 to square 2, you need to find out how easy or how closer that step takes you towards the goal of winning the chess game. Every chess player does that in order to see how desirable a move is before they actually take the move. When you are solving the Rubik's Cube, if you take the Rubik's Cube and you decide to just move and move and move and move, you could spend 100 years on it and you will never solve it. Before you make a move, you need to look at the various colors, you need to look at the positions, and then you can in your head do a sort of a forward thinking, a projection to see how closer to your solved Rubik's Cube a move will take you before you make the move. In solving a maze, usually when you have a maze on paper, you would see that in your mind's eye, you sort of trace a path in your mind. You keep tracing paths in your mind before you actually start drawing through the maze. That is an example of evaluating different moves before you carry out an action to solve a problem. Then in traveling from Kumasi to Accra, if I want to move from Kumasi to Accra, I don't need to actually sit on a bus to move from Kumasi to Accra, and I don't need to sit on a motorcycle to move from Kumasi to Accra. I don't need to have sat on a plane to move from Kumasi to Accra before I decide which the best option is. Rather, I can, by looking at my resources, my time available, my need for comfort, and some other factors that may be important to me, I could evaluate the various means of traveling to Accra, and then by so doing, choose one without actually taking the journey. That would have been an example of an intelligent search. Right. Now, in formulating search problems, we have what we call the initial state. Your initial state is going to be your starting point. So if we are talking about the traveling salesman problem, for example, the city that the salesman starts from becomes his initial state. If you are talking about a jumbled Rubik's Cube, the state of the Rubik's Cube at the time you start even before you do your first move. That is going to be your initial state. Now the goal state is going to be the end result that we want to achieve. So the place that we want to reach, the place that we want to be at the end of solving the problem, that becomes our goal state. So again, in the question of the traveling salesman, the destination city becomes the goal state, and the solved Rubik's Cube becomes the goal state of any Rubik's Cube that we want to work on. Permissible operators could be going to city X, going to city Y. It involves the various ways of moving in between our initial state and our goal state. Permissible operators involve the various moves that we can undertake in order to move from our initial state to our goal state. And in talking about the traveling salesman problem, it could be moves like go to city X or go to city Y or go to city Z. And then in the Rubik's Cube, we could have something like rotating a subcube because of the way the colors are. Those are moving, rotate left, rotate right, rotate center, rotate up, rotate down, different kinds of rotations. That will be the possible moves we can take in formulating the Rubik's Cube problem. Before we continue, we need to know what a state is and what a state space is. So in formulating problems, because we spoke about the initial state and the goal state, a state is basically just one status of a problem. That means if I am in city X, what are the conditions that are affecting my moves? What are the conditions that are affecting my ability to move closer to my goal? All those conditions will form part of one status of the problem. And so we say that a state captures all relevant information about the problem at that particular point in time or at that particular position. A state space, on the other hand, is going to embody all the possible states that we can have in solving that one problem. It's a collection of all the possible states. It includes all possible routes, and it includes all possible combinations of subcubes and moves. Now we have the types of search problems. We have the single state problem. We say that a single state problem is deterministic in that we can determine exactly how the problem will be like after we have made one move. So when you make one move, the next state of the problem can be known when you make a move. It is fully observable, meaning that when we are standing at one corner, we can have a good overview of the total problem and the total possible solution. The solution is a sequence usually, meaning that you move from A to B to C to D to E. That is how a single state problem is like. Then we have the conformant problem. As the name suggests, a conformant problem does not conform to any particular specification. So it is more or less like an unknown kind of problem. We don't know what it entails. We don't have states that we can observe. We don't have any precedents. There's no particular way to solve it. We're just going to do a random search. We're just going to move around and see what works. Solution is usually a sequence if there is a solution. Then we have the contingency problem. It is non-deterministic, meaning that when we take an action, we are not 100% sure of the result of the action that we are going to take. So we cannot say that the next state of the problem is determined by the move that we make. It is partially observable. We can't see all the things that are associated with a state from one corner. We can't do that. And different percepts. So a percept is a perception. A percept is how you see or how you view the state of a problem. New percepts provide new information about current states. So where we are, whatever we see next will give us additional information to what we already have. And the solution is usually a contingent plan or a tree. So if I am standing at point A, I may see, because I'm in point A, I may see that going from point A to point B is a possible solution. Going from point A to point C is a possible solution. From point A to point D is a possible solution. And I may even be able to go ahead to see another step beyond that. So I know that A to B is a solution. And when I'm at B, I can go to E, F, G, H. And when I am at C or D, I can go to Z. When I am here, I can go there. So it's usually in the form of a tree, and we call it a contingent problem. Then we have the exploration problem. Here, the state space is unknown. Remember we said that the state space is a collection of all the possible states of a particular problem, meaning that any possible move we can make, we can find solutions, we can find information about it. Here, we don't even know the number of moves we can make. And so it is we purely solve this problem by exploration. As we see the problem, we save the information we get about the problem. As we see a state, we save the information we see about the state. So the state space is completely unknown. If you have any questions, you may contact me on my contact details that is at the beginning of the slides. Thank you, and we shall come back with the second part of this edition.